hello everyone. My name is Pizarro. I'm a PhD student at Universidad de Chile. And today I will present you a work called The Value of Observability in Dynamic Pricing, which is a joint work with José Correa and Gustavo Vulcano. So to introduce and understand what the value of observability is, let's consider a monopoly market with one item to sell to a single buyer who arrives according to some distribution. So the main goal of the work is to understand what's the value of being able to customize the price curve upon the arrival of the customer. And to answer this question, we need to compare and consider two different settings. On one hand, we consider what we call the observable case. And this problem states as follows. So the game starts at time 0. Then nothing happens until a buyer arrives at some point of time t0. After the arrival, the seller observes the arrival of the buyer. She decides a car price to offer for the rest of the liaison, observing the valuation distribution of the buyer. After that, the buyer's valuation is realized. He observes the prices and he decides when to buy, maximizing his utility. On the other hand, the goal of the seller is to maximize the expected revenue. So the main feature of this problem is that the seller can observe the arrival of the buyer and then fix the price curve for the rest of the liaison. On the other hand, we consider the unobservable case. And in this case, the seller does not have the power of observing the arrival of the customer. And so she should fix the pricing policy since the beginning of the liaison, knowing both the arrival distribution and the valuation distribution of the buyer. After that, at some point of time, the buyer arrives, his valuation is realized, and he observes the prices for the rest of the liaison. After that, he again decides when to buy, maximizing his utility. The goal of the seller is again maximize her expected revenue. So note that in the observable case, the seller has more information than in the unobservable case, and then the seller's expected revenue in the observable case is at least the one in the unobservable one. So the main goal of the work is to understand how much better could the observable case be. And to do that, we bound what we call the value of observability. And we define the value of observability as the ratio between the expected revenue of the seller in the observable case and the expected revenue of the seller in the case where she's not able to observe the arrival. So another motivation that it's interesting to say is, okay, so now again, suppose that we are in a monopoly market, with one item to sell, but now we have unlimited inventory and a continuum of buyers. So the continuum of buyers with total mass 1 is distributed according to some distribution, and we now consider two different problems. On one hand, we consider the problem where at each point of time, the seller can bargain with each of the pool of buyers arriving at this time, and then she can offer a personalized price for each of them. So if we compute the expected revenue of the seller in this problem, we obtain the same expected revenue than in the observable case described before. On the contrary, if we consider the problem where the seller should offer the same price curve for all customers, so she should fix the price curve at the beginning of the selling horizon, this problem is equivalent to the unobservable case described before. So if we call the price of discrimination as the additional rent the seller can obtain by tracking the user through posting a personalized price, this price of discrimination is equivalent to what we call the value of observability. And then in this work, we will bound what we call the price of discrimination, that is the additional rent the seller can obtain by personalizing pricing. So about the setting, we consider only one seller who has one item to sell over an infinite time horizon. We assume that there is only one buyer who arrives according to some distribution G, and the buyer has evaluation B, that is private information, but its distribution F is well known by the seller. And we consider that the seller commits to a price function, and we also assume that both the buyer and the seller have a discount rate. And furthermore, we consider that the buyer is more impatient than the seller, and we assume that because otherwise it's well known in the literature that the optimal price is to set a fixed price, and then we don't have a dynamic problem. So about the model, the buyer arrives at some point of time. After that, he observes a price function and he decides when to buy, maximizing his utility. His utility can be computed as his valuation minus the price he pays, discounted according to his discounted rate. We also can describe the behavior of the buyer by using a function phi, and this function phi satisfies that evaluated at his purchasing time is equal to the valuation of the buyer. On the seller side, and the seller problem depends on whether we are under the observable case or the unobservable case. So if we are in the observable case, the seller observes the buyer's arrival time and then selects a price function to maximize her expected revenue. On the other hand, in the unobservable case, and the seller has not observed the arrival time, and then she pre-commits to a price functions at the beginning of the selling horizon, maximizing her expected revenue. So the observable case has been already studied in the literature, but we prove a key result that we will use for bounding the value of observability. So basically, this result states that for the observable case, where the buyer arrives at time 0, up to time log 2 over delta, where delta is the discount rate of the seller collects at least half of the expected revenue. So in other words, if we are in the observable case, where the buyer arrives at time 0, and the buyer wants to collect half of her expected revenue, it's enough to see the problem up to time log 2 over delta. So two important remarks about this time t are that on one hand, note that this time is small. So for instance, if delta equals 1, so this result states that up to time log 2, the seller collects half of her expected revenue in the observable case. And the other observation is that this value t only depends on the seller discount rate, but it doesn't depend on the other parameters of the problem. About the unobservable case, the unobservable problem is harder not only to solve, but also to model it in general. And then it's hard to obtain an explicit solution. So, however, we want to bound the value of observability, and to do that, it's enough to search for a price policy that allows us to obtain a constant fraction of the total revenue obtained in the observable case. And to do that, basically, the idea is to consider the optimal solution for the observable case and repeat it along the whole horizon. So now we are going to describe explicitly this pricing policy we will need to bound the value of observability. So the first idea was to consider the optimal solution of the observable case that we call P. And the idea is to repeat it along the whole horizon. So something like that. The thing is that to do that takes infinite time. And then to solve this problem, we use this key result. And this allows us to just, instead of repeating the whole price function, we just repeat the first t units of time. So we consider a period function of period t, with period t, where we repeat a portion of the optimal solution for the observable case. Now, considering this pricing policy, we have another issue, and the issue is that the buyer is strategic, and therefore we can compare the expected revenue in the unobservable case by considering this pricing policy with the total expected revenue in the observable case. So to fix this problem, what we do is to consider now a periodic price function, but with period 2 times t, where during the first t periods of time, we set a very high price. And after that, we implement the optimal observable pricing. And then repeat this definition along the whole horizon. So by doing that, what we obtain is that if the buyer arrives within these intervals where the price is high, then he behaves like an observable, like a buyer arriving in the observable case. And therefore, it allows us to compare the expected revenue in both cases. So this is the idea, but now we have another problem. And the problem is the arrival distribution of the buyer, because we can, the arrival distribution is arbitrary, and then we can have a distribution with a lot of mass at these points where the price is too low. So to overcome this problem, what we do is to take this pricing policy and we randomize it by doing a random shift. So by doing that, basically what we obtain is that the arrival distribution now is uniform, and then half of the time the buyer will arrive within these intervals where the price is high, and half of the time will arrive within the intervals where the price is equal to the optimal solution in the observable case. So we will use this pricing policy to bound the expected revenue in the unobservable case, and know that we are not considering all buyers. I mean, we are not considering the buyer arriving within all the horizon. We only consider the buyers arriving within the intervals where the price is constant. And also know that the price is always higher than P of t. Then if the buyer arrives but has a valuation less than this value, his utility will be negative and then he won't buy. So we consider this pricing policy and buyer arriving within these intervals where the price is high and with valuation greater than P of t. So by taking this pricing policy into account, we can upper bound the expected revenue of the seller in the unobservable case as a constant fraction of the expected revenue of the seller in the observable case. And then by computing the ratio, we obtain that the value of observability is upper bounded by a constant. We obtain this constant by taking this value of t in particular, I mean the one that allows us to collect half of the expected revenue, and then if we optimize under this parameter t, we can improve this upper bound, and we obtain our main result stating that for every valuation distribution and for every arrival distribution, the value of observability is at most a constant 4.91. So in particular, if we consider valuation distribution with monotone hazard rate, this bound improves to E, just considering a constant, the constant pricing policy. On the other hand, okay, so this analysis was to obtaining an upper bound for the value of observability, but what about a lower bound? So to obtain a lower bound, it's difficult because it's not easy to obtain an explicit solution for an observable case. But what we did is to use dynamic programming, and then by using a particular instance of an observable problem, we obtain this lower bound, and this is the best lower bound we have up to now. Okay, so some final comments. We prove that our main result is that the seller expected revenue in the observable case cannot be more than 4.91 times the seller expected revenue in the unobservable case. And this result is interesting and surprising because of several factors. So first, note that this result holds for a very general model. So this result holds for every evaluation distribution, every arrival distribution, and every both seller and buyer's discount rates. So it's very general. And on the other hand, note that we obtain a constant bound. So this bound doesn't depend on any of the parameters of the problem. So, and in general, simple pricing strategies such as fixed pricing fail to guarantee a constant bound. And that's why this result is really interesting and surprising. So about some current work and open questions, we are now working on improving these both upper and lower bounds we have. And one possible question for the future is think about whether these arguments also holds for considering multiple buyers. So that's all. Thank you.